Hey, welcome back. What is a physicist? Is it a man behind the curtain?
The great Oz has spoken. Oh, pay no attention to that man behind the curtain.
Or a caped crusader saving the world from dark forces? Great questions that demand great answers. And today we have James Kakalios, professor of physics at the University of Minnesota in Minneapolis. James thinks physicists are superheroes. Physicists aren't gods, but they do change the universe by defining how we understand everything that was already there. But they expanded our reality. Isaac Newton looked at the relationship between the moon falling to Earth and an apple falling from a tree. My question to James Kakalios today is, how does physics define you, society? And a deeper, darker question. Do we really understand the physics of the 21st century? And if we don't, why not? So, James, physicists aren't gods. Physicists don't invent the universe. Physicists, would you agree with me, define the universe?
Well, I'm not so sure about defining the universe, but certainly they have, by understanding the universe, elucidating the rules by which nature operates, we help refine our view of reality. I would probably say that the story of science in general, the story of science is the triumph of reason over common sense. So you have a common sense view of what you think the world is and how, based upon your personal experience.
Right.
And science, in digging down and trying to understand things, finds that that common sense picture is not always complete, not always accurate. Isaac Newton said, an object in motion remains in motion unless acted upon by an outside force. That is completely opposite to everyone's experience. You're driving down the highway at, say, 60 kilometers per hour, 60 miles per hour. It's not that once you go in a straight line and you're at that speed, you could take your foot off the gas and just, coast.
Right.
You will come to, you have to keep exerting energy. And
Right.
that's because you are acted upon by invisible forces, friction and air resistance, that you have to overcome. And to
Right.
balance those forces, then when there's no net force, an object in motion remains in motion. There is a world that we don't see
Right.
with naked eyes, and yet science, physics has discovered the rules by which they operate,
Right.
and that continually refines our vision of reality.
Right. Refining the vision of reality. That is so interesting. So, did an apple farmer in Lincolnshire, next door to Isaac Newton's house, see an apple fall from the tree and say it just falls? But after he read Isaac Newton's wonderful paper, how did that change the farmer's view of the apple?
Right. So there's the story of Isaac Newton and the apple. Isaac Newton, due to the Black Plague, got out of Cambridge and went out to Lincolnshire, as you say, where his family had a apple orchard.
Yeah.
It's not that an apple fell, hit Isaac Newton on the head, and he said, "Oh, there must be gravity,"
Right.
nor did the apple fall on his head and say, the force of gravity is a constant times the mass of one object times the mass of the other object divided by the square of the separation between them. But by determining the nature of the force,
Right.
and the nature, how it would affect the motion of the moon and the planets,
Right.
he was able to then connect that up to previous observations
Right.
and explain the motion of the planets. And the big thing there was to the realization that the same force that pulled the moon in towards the Earth, and it has to be pulled in towards the Earth because the moon is moving away from the Earth, and without the force of gravity, it would just fly away. But it's constantly being pulled into the Earth and constantly falling into a circular orbit.
Right.
And the stable orbit is because of this force of gravity. What Newton connected was that that same force that pulled the moon towards the Earth pulls the apple towards the Earth when it falls from the tree. And by connecting the celestial with the terrestrial, that was the tremendous leap to realize that the same forces that governed the motion of the stars and the planets governed the behavior on Earth was a tremendous leap. And that altered one's view of nature.
Yes, it altered one's view of nature. I'm really going to dig down on this with you. So that's the point, isn't it? So people saw the moon, people saw the stars, people saw apples falling, but the mechanism and why they stayed in lockstep with the Earth or the apple fell was unknown.
And to realize that there was a simple explanation that governed both phenomena that seemed so radically different. You know, an apple falling versus the moon in its orbital motion. That you would never ordinarily say that it has to be obviously the same simple expression. But to show that that was indeed the case was truly revolutionary.
It just busts all idea of scale. And then that force was incredibly useful because it started explaining our universe. It explained lots of things, which we have observed.
So another example, say, of science or physics changing our view of reality is James Clerk Maxwell, who took the previous work by Ampere, Faraday, other people, and combined it and made a crucial modification and developed Maxwell's equations. We call these four equations, which, you know, one was developed by Ampere, one was developed by Faraday, but the four together are called Maxwell's equations, correctly so, because James Clerk Maxwell realized that through these equations, if you had an oscillating electric charge, that would create an oscillating electric field, which would create an oscillating magnetic field, and that two of those together would travel at a speed that he was able to calculate was exactly the speed of light. And that means that light is an electromagnetic wave. And that was a truly, you know, that was enough, again, so what he discovered, and we now know, is, and depending on how fast you move that oscillating charge, either can get radio waves, or you can get microwaves, you can get infrared, you can get visible, ultraviolet, X-rays. It just goes on. All that depends is how fast you're shaking the charge up and down. We live in an invisible sea of electromagnetic waves. We never, I mean, the only part that's visible is a very tiny, narrow slice of possible frequencies.
Absolutely, our human perception,
We never think about the fact that we're in a sea of radio waves, for example, until you can't get a cell phone signal. They only notice it when it's gone. You never think about the fact that I could turn on my cell phone, I could turn on my radio, and it works because the radio waves are always here, and they're always in the room with you. And
but isn't that so important? Isn't in Maxwell's case, he's defining the invisible. He's explaining a force which, I mean, that is
and also to understand the understanding of light and connecting. And again, people understood waves. They had
Right.
equations for waves
Yeah.
to describe it, water waves and waves on a string, vibrating violin strings.
Yeah.
People understood waves, and to connect light, which was always thought to be something unique,
Right.
as to say that this is just another manifestation of a wave phenomena, was
Right.
also, again, the triumph of reason over common sense. You don't think of light that way, and you certainly don't think of light as being things that we can't see with the naked eye.
So I mean,
It was
it redefined how the universe of not our perception, but helped define a wider universe of a reality which we weren't, which we didn't see, but could be proven to
was
exist.
there nonetheless. What
Yeah,
was there
no, there are
nonetheless.
less, right?
And the fact that, I mean, now we make use of this in the fact, say, in night
Right.
vision gone,
Yeah.
where the fact that all of us every person is putting out as much light as, say, 100-watt light bulb,
Right.
but you don't see it with the naked eye because you're
Right.
just too cool.
Yeah.
You're if you were a little bit hotter,
Right.
you might be glowing in the visible, but you're glowing in the infrared.
Mm-hmm.
And so if you have a sensor that can detect that infrared light and then shift it
Yeah.
into the visible spectrum so that we can see it, then you
Yeah.
could see infrared objects. So to be able to do that is, these are the first steps. The basis of radio, TV,
Yeah.
Wi-Fi, cell phones. Maxwell was doing this in the 1860s
Right.
when the American Civil War was going on. And so
Yep.
you think of the American Civil War, people understood electricity and magnetism enough to have telegraphs, but this idea of the wireless, that was a
Right.
huge transition.
Right.
And so uh, those these are things that kind of also help. There are insights into how the world works that lead to technological changes that definitely change the way we think about the world.
Right. So they open up the possibility to engineers who can exploit a newly defined but pre-existing force of nature because it has been
Right.
defined.
Right.
And that's how we clever bunnies on this planet work. We need that definition, and then we can hit things hard together and make stuff which we use. Which I just
Yeah. Not always. There's at least one example where the
oh
engineers came first, and
ah
that's thermodynamics.
oh right
So engineers developed pumps and
right
engines. And it was then when the scientists were trying to figure out the ultimate efficiencies to make
right
these engines more and more efficient, that the laws of thermodynamics, the connection between
right
heat and work, all was developed. And again, these things, when I teach them in the class,
yeah
we start with the fact that matter is made of atoms, and you can think about entropy, you can think about
right
energy and work in terms of atoms moving. The fact that these scientists were able to develop thermodynamics without a knowledge of the atomic nature of matter and
right
gases and everything else is a huge testament to humanity's ability for abstract thinking. To
uh,
be for Carnot to come up with the second law, uh,
right
just in the context of water wheels, and he got it right. He nailed it, and
uh,
that is just
yeah
inspiring that people can be that
right.
insightful and clever.
Well, I mean, in some ways, and looking at the way the human body works, the pump and the pipes, and then looking at birds and flight. I mean, you could approach technology by observation of the
Right,
natural world, but
right.
but physicists define underlying laws which work and continue to work, and also continue to work off Earth, you know, in much
That is our understanding. That is our belief.
right.
That, I mean, we've never seen things which
No,
require us to abandon that.
right,
Now, there are things that we right now, such as like the expansion of the universe, the
right,
acceleration of the expansion of the universe,
yeah,
things that seem to be moving held together with gravity that we can't observe, so we call it dark matter. There are lots of open questions. And you could say, well, these laws don't work out in outer space or something, but the goal is to see, based on what we know, what is the minimum amount that we've got to add, that we've got to change in order to account for what we see? When faced with a problem or something that we don't understand, a scientist doesn't throw up their hands, they roll up their sleeves, and they get to work. Enrico Fermi said that when your observation agrees with your expectation, you've made a measurement. When your observation disagrees with your expectation, you've made a discovery. So you go in with an expectation of what you're going to see. And on your best days, you'll see something and say, huh, that shouldn't have happened.
Right.
and and of course, the first thing you need to do before you start thinking about booking trips to Stockholm is thinking, well, how did I screw this up? Because if you don't find your mistake, someone else will. And that's but that someone else will also means that we accept the notion that there is this reality that we're dealing with. And it's the same reality in Minneapolis than it is in France.
Yeah.
And it is the same that an experiment done here should also work in France.
I hope
so. Right. And so that this universality that is really just kind of like is now embedded in our worldview of how the universe works, to some extent started with Newton and connecting the apple to the moon.
Right. Yeah. Thank you, James. Yeah, exactly. You have defined the role of the physicist and the role and how it changes the invisible, makes the invisible visible for the first time, and practical applications. Moving forward to the 20th century, it seems that something happened when Albert Einstein linked E equals mc squared, and the idea of that amount of energy in matter could be liberated. The word that I'm going to use carefully here is the idea became exciting to become weaponized. It was always possible then to possibly unleash those forces as a bomb. And that technology, the atomic bomb, and all the amazing physics that went into it, and the money and everything, which changed World War II, became secret. It needed to be compartmentalized. It went into a small secret laboratory in Los Alamos or Sandia or defense contractors. My viewers are worried that physics today has become dark and compartmentalized into and hiding behind freedom of information in defense contractors. What's your view on that? And do you think something fundamentally changed in physics when the atomic bomb was developed?
Well, okay. So first, the good news. Physics hasn't changed. It hasn't gone dark. It always was dark. People have always used this knowledge of the world around us for a variety of purposes, and some of them have been military based. Now, it is certainly, there's also the question, we started with the discussion of scale with Isaac Newton. There's a difference in scale when you're dealing with with atomic weapons. And I would say, to some extent, there were two major developments during World War II that transformed our view of the world. One was the atomic bomb, for sure, the Manhattan Project, The other was the development of radar. And radar, the argument, the expression I've heard is that the radar won the war,
Yeah.
the atomic bomb ended the
And
war.
spot on.
And again, there was a great deal of concern. There was understanding that certainly the development of atomic weapons had to be secret during a war. But there was a lot of scientists, Fermi and others, after the war, believed that now the research should be kind of opened up again.
Right.
Because there were a lot of potentially beneficial applications. And we've seen this with, like, radiation treatment of diseases and cancers and other
Right.
things. An understanding of this is and at one point it was viewed that nuclear power, a clean form of energy,
Right.
certainly compared to fossil fuels. I would say that what happened at the early part of the 20th century, there was the development of relativity, special theory of relativity, general theory of relativity with Albert Einstein.
Right.
And that certainly has also impacted, without an understanding of how relativity affects the measurement of time, GPS wouldn't work. Your GPS satellites require both general and special relativity corrections in
Right.
order to get the locations of objects
Yeah.
correct. So that's very important. The really big thing that happened, to my mind, around the same time period was the development of quantum mechanics.
Right.
And
Right.
understanding quantum physics is basically the study of atoms and how they behave and how they interact with light. And a lot of the common sense rules
Right.
that we have do not apply, do not work.
In the big world and the micro. And
that's right. You start with Newton, you
Right.
go to Maxwell,
Right. Planets.
you get all of these things, you get thermodynamics,
Yeah.
but then when you finally get to quantum mechanics, things become profoundly anti-common sense.
Right.
Quantum mechanics says that an electron can move and it can have any velocity it wants if it's just moving through free space.
Right.
But if it's bound in an atom, bound to the positively charged nucleus, it can only have certain particular energies.
Right.
This is like saying that I have an automobile and I can drive at any speed I want on an open road.
Right.
But if I'm on a closed racetrack going around and around, I can only go in multiples of 10 miles per hour.
Oh, wow.
And I can only slow down from 40. I can't go from 40 to 35. I can only go from 40 to 30. And if a gust, the most amazing thing is,
Yeah.
if a gust hurricane wind behind me was going to push me from 20 to 24,
Yeah.
it has no effect. If it goes from 20 to 30, then I speed up.
Bunk to a next level. Right.
And this quantum stepping, a quantum is actually Latin for how much.
Yeah.
That this has led to the development of solid state physics,
Right.
which led to semiconductor physics, which led to the transistor, the solid state laser, the light emitting diode,
Right.
all of this, that the world we live in, and then you couple that with Maxwell's development of electromagnetism, and you have the world that we live in
today.
And why and this maybe seems a little bit more divorced from what people were doing when
yes, go ahead.
Yes. And so
why is it more divorced?
Partly because, one, the rules by which governing how these things work are quantum mechanical, so they're intrinsically counterintuitive.
Right.
But the other thing is because we've figured out how to make these devices so small that they cannot be seen with the naked eye, and thus they are not susceptible to, we can't see even the innovations that go into play. So Maxwell develops his theory of electromagnetism Hertz does a series of experiments confirming that this is indeed the case, that
Right.
radio waves can be transmitted. You get the development of radio. The initial radios were these big things, big
Yeah.
objects.
Yeah.
And while you may doubt that there are these invisible radio waves surrounding you, you can construct a radio. It's a macroscopic, large-scale device.
Right.
There are tubes in it. There are wires.
Yeah.
There are resistors and capacitors. You can build this. You can see what you're dealing with there. You build the first transistor was built 75 years ago last year.
Hey.
Now, there are in your house, I'm willing to bet, you have more transistors than there are stars in the Milky Way galaxy.
Absolutely.
And you take that, and then you multiply that by the billions of people on Earth, and the transistors are everywhere, and they are smaller and smaller. The first one was, again, a macroscopic object. You could see, right, with the wires coming down.
Pyramids. Yeah, it's great.
Yep, exactly. And now they are so small that, to some extent, this is the difficulty that those of us who do solid state physics have in communicating with the public, because the things that we're working on are in this little chip, and it is literally a black box. Right. It is a black box with these little wires coming out. But what goes on inside is invisible.
But we've just shrunk it down. And
because
we started big. Yeah.
It started big, but very soon it got. I mean, the very first integrated circuit was also a macroscopic object that you could see, and now we figured out how to shrink it down.
Right.
And so the example that I've given is Wilbur and Orville Wright.
Right.
Their first flight on Kitty Hawk, 1903.
Mm-hmm.
The first flight doesn't even last a full minute, 59 seconds.
Shorter than the interior of a 747. Yeah.
Yes. Okay, that's where I'm going. So they do this in 1903.
Yeah.
66 years later,
right,
Neil Armstrong steps on the moon. And you go from Kitty Hawk and this plane using these simple motors to Apollo 11.
I know.
If you look at the very first planes and again, this is the science and the technology being used for war. A lot of this, you look at World War I biplane, compare it to World War II planes. And then you compare it to the jumbo jets. You compare it to the Concorde. You compare it, and if you looked at that, you could see the progression of history just by visually looking at these planes and looking at the difference in scale and complexity.
Right.
If you look at a smartphone and you look at one from 20, take an Apple One and an Apple iPhone 14.
Yeah.
They look a little bit different, but you could, but it's not by like looking at a biplane and looking at a jumbo jet.
Right.
And yet the capabilities of what these things can do is, I don't know for sure that it's exactly analogous to what happened with an airplane, but it is equally dramatic. But it's not visible. You can see the evolution of flight and aviation. By looking at the planes. You can't see it by looking at these devices. And to that extent, to some extent, people think that these things are magic.
Right.
And I would say, you're right, it is magic. Now, it's not magic like Doctor Strange from the comic books. It's magic like Harry Houdini.
Right.
Who does things that seem impossible, but he's not breaking the laws of physics. He's exploiting the laws of physics in order to create these illusions.
Right.
And so it's the same way. They're exploiting the laws of physics to do things that seem impossible, but are completely possible because they exist. and they do this. So
that is brilliant. That touches exactly on the killer question. So is it possible that the that some of the unexplained that we're seeing today is just misunderstood, but all actually, of course it does, uses
Okay.
for
I personally
physics.
I personally believe that it is. There is a reason for everything that reason can discern. That
Right.
you, by using reason, as I started off and I said that the triumph of reason over common sense, that we can use the techniques of science to answer all these questions.
Right.
Now, I can't prove that that's true. There may be some problems out there that will defy science. I can think of one of them off the top of my head: consciousness, human consciousness.
Right.
It's
Fascinating.
and it's possible that we may never fully understand it
Yeah.
because you can't use consciousness to try to
Right.
you get outside of it. Just like I can't see the United States when I'm sitting here in Minneapolis. I'm
Right.
too in it to get the
Yeah. To
bigger
think
view.
of the big, to see the big picture. Yeah.
But I believe that we will eventually understand it. And in
Right.
that to that issue, I have faith.
Yeah.
And that is my faith, the faith of a scientist, that things can be understood by scientists.
Let me
Anyway,
push you on. Let me push you on magic magicians and the man behind the curtain idea. um, in the past, we've had clever brains who have understood things that has been only that knowledge has been kept by the high wizards,
yes.
the alchemists, the priests of the world,
Right.
and because of that knowledge or understanding, which is science, they have been able to get one over the rest of the populace because they can demonstrate and trick and do things that most people don't understand. Is that going on today more than it did, say, in the 19th or early 20th century? Are the advanced physics, because it's difficult, because also I think TV and broadcasters and educators are slightly failing in communicating to the public, does it offer an opportunity to bring back the wizards and the alchemists and the priests of the unknown?
This is a an important question, and it kind of guts to the issue of science outreach and
Right.
engagement with the public and science communication. So, and I've actually
Yeah.
expended a fair amount of effort
Yeah.
into these matters, right? As seen by the Physics of Superheroes, available at any major bookstore,
Right.
Amazon.
Good. Link in the
Um,
description.
so one of the problems is that the in order to understand how things work at some level, you can get like a kind of a general type of understanding,
Yeah.
but to get more of a deeper understanding, you have to do some math.
Right.
And that intimidates a great deal, many people.
Mm.
And getting to whether how math is taught in schools or other things, I don't want to get into that discussion.
Right.
It is a challenge because, for example, if I explain something that's going on in my research to one of my colleagues in the physics department, and I do a bad job explaining it,
Right.
she will say no, that she should be able to understand what I'm talking about. So she will interrupt, she'll ask questions, she'll interrogate. If I do the same bad job talking to my next door neighbor,
Yeah.
who's not a scientist, they will think they don't understand it because they're not quote unquote smart enough
Right.
when it's just that I did a lousy job explaining it. So they don't ask the same questions.
Right.
But this is the challenge for people doing science outreach is how do you keep people from getting those insecurity shields to
Right.
launch? I mean, one way would be, using superheroes, because if you're
Yeah.
talking about Spider-Man or Superman, people feel like I should be able to understand this. The more that the person who's not a scientist and engineer can understand the principles and issues at the heart of the matter, the more that they'll be able to make, as I said once before, um, decisions that are technically sound, but don't just sound technical. You want it to be. Uh, I had to say, I said before, so because I'm not that clever that I just came up with that.
Okay, no, it's a great phrase. Yeah.
Yeah, thank you. But so that is the goal. Is
Right.
it's the same reason why we believe in public education. We have public libraries because
Yeah.
the more educated a population is, one hopes, one expects that the better the decisions they will make. Now, scientists,
But has physics got away with it? Has physics launched itself into a complex mathematical system in the stratosphere, which is not being communicated well enough and could well be the unknown to the members of the public who and as I said earlier, it might be something which could be exploited by the wizards of this world.
well, fortunately, there's enough of us that no matter what you say or do, unless you can really back it up with data, you'll find colleagues who will say, nah,
Yeah.
that is just blowing smoke. Um,
Right.
and then of course, then you get to this issue that some people will throw up their hands because they say, well, this guy says something, and she says something else,
Right.
and I don't know who to believe, so who knows, right? It's like, my old grandmother, Greek immigrant, would sometimes say, doctors, what do they know?
Yeah.
But to some extent, and that's partly because no issue is ever fully resolved.
Right.
Nothing is ever done. Um, there's always more that can be gone on. And when you deal with things that are very complex, like the human body
Yeah.
or other issues, you're dealing with so many complex things that there's not ever going to be a simple, easy answer. We have made such progress that
Yes.
to some extent, some of the issues that you say are a consequence of the progress we've made, insofar as people now expect instant answers. They expect things that are 100% unequivocally, this is the way it's going to be, and that's it, and no questions asked. And then, situations change, things, evolve, and people then say, well, why should I? You said this before. You said blue yesterday, and it's green today,
Right.
and should I ever listen to you ever again? And
Right.
that
That
is,
seems I get that all the time where people say, I don't trust scientists. They change their mind. I go, that's the point. That brings me back to my final question is, when people see this quantum woo, when we see things and we're shown things by our governments, by our military, on our media, of things that we don't understand, it's just a matter of time that we do understand them. Would you say? Would you agree with me on that? It's not an unknown; it's a temporary unknown that we need to work on harder.
I absolutely do agree with that. I think if you're dealing with things like, uh UFOs or UAOs or whatever they're called now, even just like much more mundane things of like room temperature superconductivity. And
Right.
if such a thing existed, it would be totally transformative
Yeah.
to energy and energy transmission and everything else. These claims have not to date borne up,
Yeah.
and because they can't be reproduced or there's
Right.
been errors that have been found. But that's okay. That's the process working. That is
Yeah.
people weeding out the bad, and eventually, so there are some people who say don't believe it. My colleagues say don't believe it, don't believe it, don't believe it.
Right.
Eventually, maybe one of them will say, well, I was wrong. What we have to get people to, and this will be my final point here, to get people to accept or to be open to changes, the principle of that we try to teach all of our students and in the training of being a scientist is actually no mathematical expression. It's no physics principle. It is a principle that we can all internalize, but it's very, very difficult. It's 4 words. What if I'm wrong? When you see something and you see something that contradicts your worldview,
Right.
whether it's quantum, whether it's electromagnetic, invisible electromagnetic waves,
Right.
what I don't believe it. It doesn't make sense. I don't believe it. But what if I'm wrong? Could this be right? It's, as Upton Sinclair once said, it is difficult to get a person to believe something if their salary depends on them not believing it. And
Right.
but to be open to the possibility, again, you have an expectation when your observation agrees with it, it's a measurement. But to have seen something that disagrees with your expectation
Right.
is a discovery. And that is an issue of like, what if I'm wrong? And then you go back and you say, how could I have been wrong? One of my assumptions was wrong. Which one needs to change?
Right.
And that's how we progress in our understanding of the world. And that's something that you just hope that people can internalize, because this is the way to like think like a scientist, which we can all do.
Yes.
And by being open to changing our worldviews, hopefully we'll get worldviews that more align with reality.
More aligned with reality. I love it. And there's parts of the definition of reality which are still mysterious, and there's great possibilities. I love that that in the 19th century physicists said physics is finished. We've measured everything that's possible. I think it was Ernest Rutherford said, no. The minutiae of measurement reveals a new physics, and he was so right.
Right? As Robert Heinlein, the science fiction author, once said,
Yeah.
live and learn, or you don't live long.
James, it's fantastic. It is such a pleasure to talk to a real physicist on real subjects. And thank you for being so open and also open-minded and with so much historic data about physics, because I think it is so important. And it's so important that we communicate properly what's gone on in the past, how it affects us today, and how to understand the future.
Because it is not separate from humanity or society. We are part of it. It is humanity. It is society. Yes, absolutely.
All right, well,
thank you very much. It's been a pleasure indeed.
Oh, that was great. I really enjoyed that. And I really pushed James on topics which I thought he might feel a bit uncomfortable about discussing, but he gave great answers. So if you want to know more about physics superheroes, read James's books. If this is the kind of film that you enjoy, give it a thumbs up, because there's more interviews like this coming up. The truth is out there.